Hello and welcome. So in this video, we're going to be talking about equilibrium vectors of Markov chains. Okay, so when we look at a Markov chain, we take this idea of a initial probability vector, and as we transition from state to state to state, we want to kind of think about what's going to happen in the long run as we get larger and larger. What's going to happen to the trend? Is it going to change consistently? Is it eventually going to stay the same? What would occur? So when we have a transition matrix, instead of trying to do that by repetition, by trial and error, one of the things that we can do is that we could calculate what's called an equilibrium vector. So an equilibrium vector is a vector, a probability vector, that as our number of repetitions gets larger, larger, and larger, at what point would the chain come into equilibrium and it would stay the same and not change whatsoever? So in order to do this, we need three things. We need v, lowercase v, which is any probability vector. Then we need p, which is just a transition matrix, regular or irregular, doesn't matter. And then we have n, so n represents the number of repetitions of an experiment. So if I take this probability vector v and I multiply it by the transition matrix to the n power, eventually what's going to happen is that that's going to reach this capital V, and this capital V represents this equilibrium vector. Now, with that said, here we're going to focus more on regular Markov chains. So the idea is that if a Markov chain with transition matrix P is regular, then we could calculate that this equilibrium vector times the transition matrix P is always going to be just that equilibrium vector. So for example, they'll give me a Markov chain. They'll say P equals, and we're going to do 2 by 2. So 0.8, 0.2, 0.35, and 0.65. And the directions will say find the equilibrium vector for this given Markov chain. If I were to calculate P and P squared, we end up with all positive entries. Therefore, it is a regular Markov chain. Okay. So we're going to use this idea here because it is regular that this equilibrium vector V times the transition matrix P is equal to the equilibrium vector V. So we're going to let our equilibrium vector, because this is a 2 by 2, our vector is going to be a 1 by 1, and we'll call it V1 and V2. So we're going to set up this V times P equals V. So it'd be V1, V2 times the transition matrix 0.8, 0.2, 0.35, 0.65 is equal to this V1, V2 vector. Okay. So with that said, now what I can do is I can go ahead and solve this system. So when we solve this, we end up with 0.8 V1 plus 0.35 V2 and then we end up with 0.2 V1 plus 0.65 V2, and that's equal to V1, V2. Okay. Now, what ends up happening here is when I simplify this, we end up with 0.8 V1 plus 0.35 V2 is equal to V1, and we end up with 0.2 V1 plus 0.65 V2 is equal to V2. Okay, so now I want to set these equal to 0. So when I set these equal to 0, we end up with 0.2 V1, negative 0.2 V1, plus 0.35 V2 is equal to 0, and we end up with 0.2 V1 plus 0.65 V2 is equal to, or not 0.65, we end up with negative 0.35. Is equal to 0. Okay. Now, here's the catch. When I look at this, notice essentially that these are the same equation. So if I continue to go on and solve the system, it's not really going to do us any good. But this will help give us one of the equations to use. If I go back to this probability vector, this B, remember that all probabilities of a given situation always add up to 1. So here, based on this, we know that B1 plus B2, that's going to add up to 1. So now I can use this equation and this equation to solve the system in order to find our equilibrium vector. So we have V1 plus V2 is equal to 1, and we have negative 0.2 V1 plus 0.35 V2 is equal to 0. So now I can solve the system. And when we solve a system of equations from a matrix, again, you have several options available to you. You can do echelon method, Gauss-Jordan method. Those are probably the two that will work the best here. If it's a 2 by 2, go with the echelon method. If you end up getting 3 by 3 or higher, then you can go Gauss-Jordan. Okay, so I'm going to solve this matrix by doing the echelon method. So I notice that, oh, look, that's a negative. So I'm going to do 0.2 times row 1. I'm going to add it to row 2, and I'm going to replace it in row 2. So when I do that, I end up with V1 plus V2 equals 1, and I end up with 0.55 V2 equals 0.2. Well, I can easily solve that equation. I could divide both sides by 0.55. So when I divide both sides by 0.55, we end up with a V2 vector of being 4/11ths, which is approximately equal to 0.3636. So now that I know what V2 is, now I can solve for V1. So V1 plus 4/11ths is equal to 1. So when I subtract 4/11ths from both sides, we end up with 7/11ths, which is approximately equal to 0.6364. Wonderful. So therefore, our equilibrium vector eventually is going to be 0.6364, 0.3636. So again, what that means is that if I start with an initial state and I run through repetitions of a transition matrix, eventually it's going to reach equilibrium when it gets to this point. That's what that tells us. Okay. So now we have some properties of a regular Markov chain. Okay. So these properties are this. So as n gets larger and larger, then what happens is that this initial vector v times repetitive powers of the transition matrix will eventually approach this equilibrium vector v. We also know that from before that this equilibrium vector v times the transition matrix itself is just equal to the equilibrium vector. So to find v, to find the equilibrium vector, we use the idea that v times p is equal to v, and that the probabilities add up to 1. And then, last but not least, we know that the powers of p to the n come closer and closer to a matrix whose rows are made up of v, are made up of entries of v. So those are the properties of a regular Markov chain. Okay. So, for example, we're going to step up our game here. They're going to give me a transition matrix K. And we're going to have 0.2, 0.6, 0.2, 0.1, 0.1, 0.8, and then 0.3, 0.3, 0.4. And they're going to say find equilibrium vector for this matrix. Okay. So normally the first thing we would check is it regular? Well, I look, are all the entries positive? The answer is yes, so therefore it's irregular. That's the first check. Is it regular? It is. So we're going to let V represent our equilibrium vector V1, V2, V3. So now we're going to say V times K is equal to V. So we're going to do V1, V2, V3 times K, 0.2, 0.6, 0.2, 0.1, 0.1, 0.8, 0.3, 0.3, 0.4. And that's going to be equal to V1, V2, V3. Okay. So now what I can do here is that when I take this initial vector and I multiply it by each column, we end up with the following. So we end up with 0.2 v1 plus 0.1 v2 plus 0.3 v3. That's the first entry. And then we have 0.6 v1, 0.1 v2 plus 0.3 v3. And then we have 0.2 v1 plus 0.8 v2 plus 0.4 v3. And that's equal to v1, v2, v3. Okay, so now I'm going to set up the system of equations to use. So we have 0.2 v1 plus 0.1 v2 plus 0.3 v3 is equal to v1. Then we have 0.6 v1 plus 0.1 v2 plus 0.3 v3. That's equal to v2. And then we have 0.2 v1 plus 0.8 v2 plus 0.4 v3. And that's equal to v3. So now I'm going to simplify this by setting everything equal to 0. So when we do that, we end up with negative 0.8 v1 plus 0.1 v2 plus 0.3 v3 is equal to 0. And then we end up with 0.6 v1 minus 0.9 v2 plus 0.3 v3 is equal to 0. And then we end up with 0.2 v1 plus 0.8 v2 minus 0.6 v3 is equal to 0. Okay. So here we are. But don't forget that, remember that this v, this is a vector also where v1 plus v2 plus v3 is equal to 1. So v1 plus v2 plus v3 is equal to 1. Okay, so we have our system set up. So now we got to solve it. So to solve this system, we set up our matrix. The best method here is going to be Gauss-Jordan. So we have negative 0.8, 0.1, 0.3, 0, 0.6, negative 0.9, 0.3, 0, 0.2, 0.8, negative 0.6, 0, and then we have 1, 1, 1, 1. Okay. All right, so Gauss-Jordan basically says that I've got to go through, and there's various steps that I have to go through to solve this. Just a hint, what I would do first here is basically I would move this row up to the top. So 1, 1, 1, 0, 0.6, negative 0.9, 0.3, 0, 0.2, 0.8, negative 0.6. Let me go back and fix that really quick because I just made a mistake and I just realized it. I was trying to copy over rows. Let me fix that really quickly. Okay. So, negative 0.8, 0.1, 0.30, 0.6, negative 0.9, 0.30, and then 0.2, 0.8, negative 0.60. Okay, so if I set it up this way, it's going to help us be easier because we've already got the 1 up here in the top left position in the top left entry. So now we can use our row reduction method, the Gauss-Jordan method, in order to simplify this matrix. So when you solve this matrix, it's 11 steps. So I'm not going to work the whole thing out. But essentially, when you solve the matrix, we end up getting a probability vector of 5/23, 7/23, and 11/23. So if we write these out as decimals rounded to 4 places, we end up with an approximation of 0.2174, 0.3043, and 0.4783. Okay. If you want to do a review of Gauss-Jordan where we actually work this out, send me an email. We'll set up a Google Meet, and we'll do it together. So what does that tell us? Well, that tells us that as we transition through n repetitions of this experiment, we will reach equilibrium at this point. Once we get to here, we're done. It's at equilibrium. All right. So as always, if you have any questions, feel free to email me, ask your questions through email, or send me a message or email me asking to do Google Meet. That's the end of this video for Markov chains, for regular Markov chains. And the next set of videos, which you will see tomorrow posted, we'll be talking about absorbing Markov chains. Until then, have a great day, and we'll see you later.